the recording now. Okay, so here we have a voltage. A voltage in a simple electrical circuit is slowly decreasing as the battery wears out. The resistance R is slowly increasing as the resistor heats up. Okay, so what we're going to do, we want to use Ohm's law to find how the current is changing at the instant, when resistance is 400 ohms, current I is 0.08 amperes, and the rate of voltage is equal to negative 0.01 volts per second, and the rate of the resistance is 0.03 ohms per second. Okay, so does it make sense that dV dt is equal to a negative rate? The rate's negative, dV dt. In the context of this problem, should dV dt be negative? Absolutely, because the voltage is decreasing. And what about the rate with respect to resistance? Should it be positive? Absolutely, because the resistance is slowly increasing. Okay, now here's what we want to find, right? Well, I mean, what are we looking to find here? We're looking to find what? Okay. I'll just say everything, Noah, everything. Okay, I don't have a chance to chat that to you, but everything. See me after class on that, okay? If you have any questions, but okay, excellent, excellent. So that's right, good, Ellie. Di dt, di dt. So, okay. How do we find di dt? Well, first of all, is I directly a function of time? Based on the Ohm's law, V equals I times R, I is equal to V over R. So, well, when I say, first of all, current is a function of, okay, based on this, that's right, Ellie, it's a function of the voltage and the resistance. But voltage and resistance, that's correct, Ian, that's exactly right. That's exactly right. Voltage and resistance are functions of that's right, Charles, functions of t. Okay, so our little chart here, and let me just try to kind of clean this up a little bit. One moment. Hold on, everybody. T and T. So the current is a function of two variables, voltage and resistance. And all that makes this a if we're looking for the rate of change of the current, that makes this automatically a multivariable problem, because the current I is a function of two variables, not one. But voltage and resistance are themselves functions of time. So we're going to use a chain rule, but the chain rule that we use is going to have to be based on this relationship of the current to the voltage and resistant, and then the voltage and resistant, their relationship to the time. So here's the chain rule we need to use. Okay, here's the of course I showed this on the previous page, and I showed this flow chart on the previous page. And this here is the chain rule that we need to use. Okay, that's the chain rule that we need to use. So notice that in terms of units, okay, what would the units be for this rate, di dt? The units are going to be what? That's right. Good, Charles. They'll be amperes over seconds. So that means in the chain rule, the rate, when I compute the chain rule, I have to have units of amperes over seconds. Well, the volts, the change in voltage here, that's in volts. So the volts cancel, and the change in resistance here, that's in ohms. So the ohms cancel, leaving you with amperes per second. This is a way to sort of check, one way to check if you're having an applied problem that your chain rule is right. So again, what we do is the partial of I, the partial derivative of I with respect to V, and the partial derivative of I with respect to R, those are based on the first chains, in the first link in the first links in the chain. But then we can't stop there, because the voltage and resistance are dependent on current. That's the second link in the chain. And so we get this. And that's the chain rule. Well, think of it like this. Think of it like this. Think of it like this. So the current varies as a function of voltage, but the voltage varies as a function of time. And then the current varies as the resistance varies, but then resistance varies as time varies. So by multiplying these out the way, you're left with di dt effectively. Well, okay, so the addition comes because the rates are additive. I'll give you an analogy. I got an analogy I like to use. Think of like a wobbly chair. Okay, think of a wobbly chair, and maybe I can draw a picture just of a chair here. It's a good question Ian's asking. Okay, so here's my chair. Has 4 legs. Okay. Now let's say that well, we've got to be a little careful on that, Charles. Got to be a little careful on that. Let's take my little chair here on the right. I'm going to give you an intuitive feel why we add these two pieces. So if I want to know how the rate at which the chair is wobbling, if there's just one leg that wobbles, like, okay, a chair wobbles if it has wobbly legs. Let's say there's just one wobbly leg. Would you agree that the chair's wobbling is dependent just on the one leg? if there's one wobbly leg, and that the rate at which the chair wobbles is dependent on the rate at which the one leg wobbles? Would you agree with that? Okay, makes intuitive sense. Okay. Now hold on here. Makes intuitive sense. Okay. And all right. And so now let's say that you have two wobbly legs. Would the rate at which the chair wobbles, could we think of the net rate at which the chair wobbles to be, would both legs wobbling affect the rate at which the chair wobbles? Would it be like an additive effect? In other words, two wobbly legs affects the rate more than just one wobbly leg. There you go. That's okay. Now Ellie's comfortable. That's intuitive thinking, everybody. Intuitive thinking. Good. Okay. I mean, you know, the book can do proofs and things like that. The book does actually show some proofs based on like epsilon proofs, but let's just keep it simple. Okay. Sometimes intuition is very valuable. Okay. All right. So now we continue here. The partial derivative of I with respect to V is 1 over R. I'm leaving dv dt there. And the partial derivative of I with respect to R is negative V times R to the negative second. And I'm leaving dr dt alone. Now you notice also in the chain rule class, I have dv dt here. Why don't I have partial of V with respect to t? I don't have partial of V with respect to t here. I don't have that. I have dv dt. Why is that? That's good. That's right, Ellie. V is a function only of time. So dv dt. And R is a function only of time. So dr dt. I only use partial derivatives when my variable is a function of multiple variables. Okay. Like the current I is a function of voltage and resistance. So I use a partial derivative for the rate of change. Okay, so we continue working this problem out here. And I end up getting that the partial derivative, or the derivative, di dt, because ultimately, based on the flow chart here, ultimately current is a function of time, and this gives the relationship. So all I need to do now, well, I'm told that dv dt is 1 over 400 ohms, and I know the current is 0.08. And well, hold on. Yeah, the current's 0.08, and the resistance is 400. Current's 0.08 amperes. Resistance is 400 ohms. And then, you know, I'm given this rate here, and I'm given this rate here. And notice that. Let me just see here. One moment. So I'm left with negative 0.000031 amperes per second. And I make a note here. You might be wondering, okay, in terms of units, okay, the ohms cancel here, or simplify out there, giving me amperes over seconds, right? Here, the voltage is equal in terms of units. Voltage is amperes times ohms, right? Because by Ohm's law, voltage is equal to current times resistance. So in terms of units, that's amperes times ohms. And so the ohms here simplifies with the ohms here. And incidentally, this, simplifies with the ohms there. And therefore, my units are good. Okay. Are there any questions on this? Okay, if not, let's go forward and look at another problem. Let's do another problem. Okay, let me give you a moment to copy this example down. Okay, we'll go over it in just a moment here. Okay, so here U is a function of how many variables? Three variables, that's right. So I'm going to make a flow chart here. U is a function of X, Y, and Z. Okay, but we want the value, we want the rate which u varies with respect to s. So we need another level on our flow chart. What's x a function of? That's right, r, s, and t. That's right, Ian. Y is also a function of r, s, and t. And z is a function of r, s, and t. So let me ask you, I'm gonna go to the solution in a moment, but can you write out the flow chart? I mean, no, we got the flow chart, but can you write out the chain rule based on the flow chart? You want to give it a try before we go to the solution? I'll give you a moment here. All right, who thinks they have it? Oh, I'm sorry. I need to give you a little more time. Hold on. Okay, who thinks they have it? Maybe give me a thumbs up, and then I'll go to the next page here. Let me ask you this: how many links are there? How many links are there? How many links are there in the chain rule for this problem? How many? Or I should say, how many pieces are there to the chain rule for this problem? Okay, Ian's thinking maybe pretty big number there, 9. Ellie's saying 3 products of 2 each. Well, let's check it out. Let's check it out. You're all learning. I appreciate all responses. This is the rule. So that's right, Ellie. So now notice here, but I know what you were thinking, Ian. I know what you were thinking. Look here at the first thing here. So we want the partial derivative of u with respect to s. Okay, let me get that. We want the partial derivative of u with respect to s. So on the first level here, u is a function of x, y, and z. So I gotta have, in other words, u is dependent on x, y, and z. So how x, y, and z varies will determine how u varies. So I gotta have these 3 pieces. But x is dependent on r, s, and t. Okay, but I don't care. I mean, since I'm doing the partial derivative of u with respect to x, I care how x depends on s. How does x vary with s? Okay, and then for the partial derivative, this second piece of the chain, we look at how u varies with y, but then I want to know how y varies with s. And I multiply those 2 rates together, and then the simplification will give me partial of u over partial of s, effectively. Okay, I mean, I want to be a little careful. I'm not saying it's quite that simple, but I'm just trying to give you an intuitive feel. And then the third piece of the chain, partial of u with respect to z. Okay, well, how does z vary with s? Okay, so you see, like in the end, you're left with rates of change of u with respect to x. Does this make sense? The first, I mean, does this make sense? This chain rule that I've written down. Okay, good. Please let me know if you have any questions. All right, well, now I compute the partial derivatives, and notice there's that why don't I have dx ds here? I have the partial derivative of x with respect to x, but I don't have dx ds. Okay, why don't I have dx ds? That's right. Good. That's right, Charles. X is a function of r, s, and t. Okay, so x is a function of multiple variables. So I have partial derivatives. Now I compute the partial derivatives that I need to compute. And keep in mind, now I want to find this partial derivative of u with respect to x when r equals 2, s equals 1, and t equals 0. Now, you know what sometimes I've seen students do? They get to this step, and what they do is they substitute in for like 4x cubed y. They'll substitute in that x is equal to r times s times e to the t, and y is equal to r times s squared times e to the negative t. They'll substitute that in, and they'll get this huge function here of r, s, and t. And sometimes you might need to do that, but you don't need to do that here. Just evaluate what x is, what y is, and what z is for when r equals 2, s equals 1, and t equals 0. And then, substitute everything in this formula here. Okay? So it'll make your life a little easier. And in the end, the answer is going to be 192. And I've shown some steps here how I got the 64. How do I get the 64? Well, remember the the first thing you compute is 4 times x cubed times y. Well, we established that x is 2 and y is 2, so that's 4 times 2 cubed times 2. That's how you get the 64. And then the 16 here, how do you get the 16? Well, you have here on the second piece of the chain rule, you have x to the 4th plus 2y times z cubed. That's just equal to 2 to the 4th plus 2 times 0 cubed. That's 16. The third one, I didn't really show any work on that. Hopefully this is enough for you to get the idea. right, are there any questions on this problem? Maybe give me a thumbs up if you're okay with that. Okay, Juliana's good. All right, Ian and Ellie are good. Okay. All right, I want to now go into the ebook a little bit and look at a little bit more of section 11.5. Are there any questions before we move on? All right, let me get the ebook up one moment. Hold on. Got to go in fresh here. One moment here. Okay, let me show you here in the book. So in the book, they give you different cases of the chain rule. And they like here, case 1, if z is a function of x and y, and x and y are functions of t, this is the chain rule. And we actually did this for the first example, except our z function was the current. It was I, so we did di dt. But the thing is, and they give a proof. You're welcome to look at the proofs. I feel it's very helpful to just draw the flow chart, and now you do have an intuitive feel for why the chain rule works. We discussed that the wobbly chair example there, which I like to use, and I think actually I'm sure people have used that idea, but I made up that idea because I'm glad it seems to be helpful to you. I'm sure there are other good intuitive examples, but generally, like the book gives different cases for the chain rule, but you don't want to have to memorize the different chain rule cases, right? You don't want to have to memorize all the different chain rule cases. I mean, let me see here. Well, hold on here. Yeah, there's one chain rule. I'm just going down here. Okay, here's another chain rule case. And so long as you draw the flow chart, you don't have to remember any of these cases for the chain rule. You just write the flow chart down, and it's easy, right? So just keep that in mind. Keep that in mind. Let me see here now. There was general version of the chain rule. Okay. There was something I wanted to show you. We're not going to likely get into this too much, but example 7 in section 11.5 shows how to do a second derivative based on the chain rule. Okay, and you're welcome to look at that. If I were to give a homework problem based on that, I would certainly make it one where there were like a guided, like a watch it video, or some kind of help aid, a master it or something. But I just thought you should see that you can look at example 7 if you want to see how, when you have a function of multiple variables, how the chain rules apply to get a second derivative, right? That's important. I mean, it's at least important to be aware of it, okay? It's very tight. It's kind of labor intensive to get the answer. It can take time. See here how they compute. What do you think of that? What do you think of that, class? The second partial derivative of z with respect to r, when z is a function of x and y, and x and y are functions of r and s. That's how you get your answer. Okay, so it is possible. And they justify in example 7. They have a flow chart here. They have a flow chart that they use. So it is understandable. Okay, it's not like it's not understandable, but it just takes so long to compute those second derivatives that, you know, I might like give you one problem in the homework, and maybe on your next exam maybe one problem, but you know, it'll be limited. Okay, now one more thing here. Implicit differentiation. Okay, so the chain rule allows us to get formulas that allow us to compute derivatives nicely based on implicit differentiation. So, like for instance, if you have a function, okay, let me try to. Can I highlight this? Will it let me highlight it? Yeah, if you have a function of x and y, but y itself is a function of x, then you can apply the chain rule. You can apply the chain rule as they show you here. Okay, because what happens, let me just show you this on the whiteboard. Okay, so you have a function of x and y. Well, let me be more clear here. You have a function of x and y, but y is a function of x itself. Okay, and you're setting it equal to 0. So in terms of the flow chart, the big function f is a function of x and f of x, and then x is a function of itself, right? And f of x is a function of x. Okay, so what happens then? What happens is, can't control this. Hold on. Hold on. Just give me a moment. So I'm almost done here, class. Just give me a moment or two. Maybe 3, okay? Let's just get this done. So in terms of the, you know, you have here f of xy. If you set it equal to 0, and you take the partial derivative of f with respect to x, okay, you're going to get a 0 on the right side. Here's what you're going to get. On the left side, based on the flow chart, here, okay, you're going to have partial derivative of big F with respect to x times dx, okay, which incidentally is just equal to 1, plus the partial derivative of big F with respect to y, but y is a function of x. Okay, so, you know, put a times there. And so what happens is you can solve this for dy dx. So what you're used to doing is when you're given, you can solve that for dy dx. Okay, and let me go back to the book and show you that. So, you know, this is what I just showed you. And if you solve it for dy dx, okay, if you solve it for dy dx, then you get this formula here. So in other words, in calculus 1, when you did implicit differentiation, I mean, basically we've derived a formula to find dy dx for an equation. And normally you did implicit differentiation like in calculus 1 for that. But now you have a formula to handle that. Okay, by the fact that you know the chain rule for a function of multiple variables. And so like in example 8 here, okay, how many recall this kind of problem? We're almost done here. Just give me one more minute, class. I thank you for your patience. How many recall this kind of problem? Like what I see, like what you see here. Find y prime if x cubed, find y prime if x cubed plus y cubed equals 6 times xy. How many recall like doing d dx of both sides of that equation in calculus 1 in implicit differentiation? How many of you recall that? Maybe give me a thumbs up if you recall that. Just the standard implicit differentiation in calculus 1. If you had, yeah, so you would use that, right, Charles and Juliana, in calculus 1. But now you have a formula, and Juliana, that's right. Now you have a formula that allows you to get that derivative. Okay? Because you have knowledge of multivariable calculus, you can come up with a formula. So I'm sorry you didn't have that formula in calculus 1, but you needed multivariable calculus to get that formula. Okay, so there you go. There you go. Are there any questions on that example? Who's comfortable? Maybe give me a thumbs up if you're comfortable. Okay, good, good. Let me see, hold on. 2 people gave the thumbs up, but I didn't see it. Ellie and Charles. Okay, great. And then, you know, I'll end this. Here's like a couple more, you know, a couple more formulas, and they show, you know, you can, if you have a function of 3 variables, you can do the same thing. So I'm going to stop there. You can look at example 8, after example 8, and they show how to derive these equations. Okay, I will stop recording.